Okay, so then for our next speaker, I'm happy to introduce Fritz Gestesi from Baylor, who's going to speak about essential self-adjointness for a class of pseudo-differential operators perturbed by strongly singular potential coefficients.
Thank you very much. So I would like to start by thanking all organizers, Christoph, Jonathan, and Renal, for organizing this event and for letting me participate. So I thought I'll talk about a class of strongly singular operators and their self-adjointness. So here's a quick list of content. Maybe we go to this page. So in many ways, I'm going to look at strongly singular homogeneous differential operators. So if you want the analog of Bessel type operators that we saw a lot about today. And then I'll do something similar in a more general case. So we will look at powers of differential operators, ordinary ones, partial ones, and eventually fractional powers. And all of this should be perturbed eventually by strongly singular homogeneous potential type coefficients. So as you can see, I'm going to start with the ODE case on a half-line, then go to PD situations, eventually discuss self-adjointness, where you look at C0 infinity of Rn minus a discrete subset. And then at the last point, I'm going to perturb that by a homogeneous potential coefficient that would look like a constant times mod x to the minus 2s. So here's a typical ODE situation. We will look at, indeed, the very first of these examples is the Bessel operator. So you have d2 by dx squared with a minus plus c over x squared, and you introduce this. Everything is going to be in L2. You introduce this on C0 infinity of the open interval 0 infinity. And then a little later, we're going to look at higher order objects, still homogeneous. You see that I have the 2mth derivative and then a c over x to the 2m, still on a half-line. Whenever you see an m in the future, it counts the powers of Laplacians. So the PDE case looks like the second line here. So we take a power of the Laplacian, and then we add a c with mod x to the minus 2m. And since this is quite singular at the origin, we try to define it on C0 infinity of Rn minus the origin. Again, everything that we do in this context is in L2 of Rn. If you don't see a measure, it's always a big measure. Now, in the end, we're going to look at fractional powers. And we do this in a fairly general situation. We not only take out a point, like here the origin, but we're going to take out a discrete set. And there are no further conditions on this, which is perhaps a bit surprising. One might think you might need a minimal distance between the points or so, but no. In the end, this works for an arbitrary discrete subset of Rn. Now, what we really would like to do is, you see on the bottom here, so I would like to have a fractional power of the Laplacian and then a multi-center singular situation. And so there are coefficients Cj, the singularities are of course at xj, and you sum over an index set, and all of these should be chosen appropriately. So the emphasis is on appropriately, which of course ideally would be as little restrictions as possible. Anyway, that's something for the future, so I won't have much to say about the last part. So let's start with the ODE situation. So we look at a 2mth order operator plus c over x to the 2m on the half-line. And here is a question that arises here, namely for which values of C is this object Tm of C, so the differential expression defined on C0 infinity, essentially self-adjoint in L2. So defined on this small set C0 infinity of the open interval. So I see this sentence. For brevity, we will jump directly to the answer on page 14. There is something went wrong, so I opened the wrong file, but I think it will work, yes. So here's the jump. Here's the result of the question I just asked. So for any m, so remember these are the powers of the Laplacian. For any m, you can find a positive constant Cm such that the number of solutions of L2 solutions, which is equal to m. So let me jump forward. Yeah, so this is unfortunately the wrong, I'm sorry, this is the wrong file, but it won't matter much. Let's ignore this part, and here's the answer for essentially self-adjointness. So the situation is for an ODE case like this, so this is my differential operator, you always have a Cm so that you are essentially self-adjoint in L2 if and only if C is large or equal to that Cm. I will give you a few of the C's on the next page. The very first one, so when m is 1, is well known, is of course 3/4, and that played a role in Jan Derezinski's talk today. We have a lower bound for this number Cm. So here's the lower bound, and you can see it grows quite quickly as m grows. So what I like to call this result is that there are no islands of non-essential self-adjointness, because you could imagine that for a C interval, and by C I mean this C here, for a C interval of a certain given one, you are essentially self-adjoint. For an adjacent interval, you are not, then you are again essentially self-adjoint, and so on. What this result says is no. In this ODE context, this is not true in the PDE context, but in this ODE context, you always have a half-line from Cm to infinity above which you are essentially self-adjoint, and you are not essentially self-adjoint if you're below Cm. So here is actually the promised list of C's one can compute explicitly. You can do the first four, then eventually you run into the problem of the quintic. So you can, as I showed you, have a lower bound for all these CMs, but one cannot explicitly write them down as they are solutions of polynomial equations. All right, so once again, the first one is the famous Bessel operator. And if you go from m equals 1 to m equals 2, you already jump from 3/4 to 45. So it goes up very quickly. Let's take a look at the corresponding PDE situation. Well, again, we have powers of the Laplacian, and we want to add a strongly singular homogeneous potential coefficient. And so you can do a standard separation of variables argument, so polar coordinates, if you want, multidimensional ones. Then you realize that the operator Tm is essentially self-adjoint, again in L2 over Rn, if and only if now a sequence of ODE operators is essentially self-adjoint. And the sequence looks like this. So you have powers of this object, that's a Bessel operator to the power m, and then you have an additional C over R to the 2m. You can sort of ignore the rest of this. I have a few hints that to analyze this and figure out when this is essentially self-adjoint, you actually need to go a little outside of our typical analysis environment. You need the geometry of certain polynomials. So there's an algebraic question underlying here. And one introduces this kind of discriminant D associated with our tau Mn, and it turns out we are essentially self-adjoint if and only if half of the roots, dm is of order 2m, as you can see, as a polynomial. Sorry, this jumped forward. If exactly half of them have real part less or equal to minus a half. Where does the minus a half come from? Well, we want L2 solutions. And clearly, when you're on a half line, at infinity, there's no issue whatsoever. Our coefficient, our homogeneous coefficient, goes to 0, so it's bounded. So you will never get a non-essential self-adjointness result from infinity. The problem is, of course, at 0, where you are singular. And not near 0, when you have a power, then, of course, so let's say x to the alpha, then if alpha is minus a half and you square, you get 1 over x. That's logarithmically divergent. So this is the borderline. So that explains why minus a half here is the borderline. Then what we do is we look at the zeros of this polynomial. We order them with respect to their real part. You can make a few general you can make a few assertions here, like when c goes to minus infinity or when c goes to plus infinity. That's probably not so important. Let me introduce an object gamma that you will see a little bit later on. It is the maximum of all the constants c. The c is in the 0 of that polynomial, so that the real part equals minus a half. So when you cross minus a half, as c varies. And it turns out that if the c in our differential expression is larger or equal to gamma MNL, defined as here, then you are essentially self-adjoint. And actually the if for m between 1 and 3 can be turned into an if and only if, but it's not true in general. Just to show you that certain algebraic objects play a role in the analysis, I mentioned the introduction of a Hurwitz matrix that's underlying this polynomial D, or the discriminant. I will later on show you in the case m equals 2 an explicit example of this, but I want to gloss over that right now. So let's go to results. Again, we're going to start with the simplest possible case. So m is 1, just a first power of the Laplacian. And we perturb it by the c over x squared, right? So this is the m equals 1 case. If you now look at the sequence of ODE operators, well, that really is a sequence of Bessel type operators. So it's easy enough to analyze this. They are all of the form minus d2 by the r squared plus c1 over r squared with various c1s depending on n and angular momentum L. And so we know again from Jan Dzerzhinsky's talk today that such an operator tau1 would be essentially self-adjoint when restricted to C0 infinity of the positive open half-line in L2 if and only if C1 is larger or equal to 3/4. All right, this should now be applied to this sequence of Bessel type operators tau1 and L. And if you do that, you get a well-known result. So this is an n-dimensional result. It says T1, so minus Laplacian plus c over mod x squared, is essentially self-adjoint in L2 when defined on C0 infinity of Rn minus the origin. If and only if, so this is best possible, your constant c is lower bounded by minus n times n minus 4 over 4 in the space dimension. Now, a particularly interesting case is, of course, when c is 0, then you're just looking at the Laplacian defined on C0 infinity of Rn, and you take an arbitrary point, in this case the origin, out of Rn. It turns out this works if and only if n is larger or equal to 4. So this is not essentially self-adjoint in 1, 2, or 3 space dimensions, but it becomes essentially self-adjoint from 4 and higher dimensions. Everything you see on this page is a classical result, so it's of course well known. This changes a bit if we go to the next case. Suppose m is 2. Well, in that case, we have now the Laplacian squared, and then plus c over mod x to the minus 4, to the power 4. Well, this time the sequence of taus, the ODE, differential operators, contains a square of a Bessel operator, and then, of course, the perturbation c over r to the 4th. And so, in a sense, it makes a lot of sense to change this into a two-parameter family of fourth-order homogeneous, strongly singular differential expressions that you see here. Tau 2 depends on C1 and C2. Again, you can play games with a discriminant. The discriminant is explicitly written down here. You see how you get it. You apply tau on powers of r, and then it's not an eigenfunction. You get c minus 4, but still the zeros of this object, when you do get an eigenfunction, a generalized eigenfunction, will of course play a role. These are the alphas that we had a little earlier, which I ordered corresponding to their real part. Here's, by the way, in this explicit example, the Hurwitz matrix that I mentioned earlier. I said I will give you an example where m is 2. In any case, one can go back to tau 2 with these two parameters, C1 and C2, and one realizes this object, defined on C0 infinity of the positive half-line, is essentially self-adjoint in L2 of the half-line, if and only if C2 satisfies this inequality. And you have to make a difference whether C1 is larger or equal to minus 11 over 4 or less than minus 11 over 4. And you can see, of course, the family that we have to look at is a special case of this two-parameter tau2 C1 C2 family. I have the values for C1 and C2 written down there on the bottom. Well, now you can analyze when tau2, this sequence of ODE operators, is essentially self-adjoint. It's the fact if and only if the constant c is larger or equal to these gammas that I mentioned earlier that I said we would come back to. Here are the gammas explicitly. It turns out the only interesting one is when L is equals 0, because all the others are less than that. And so this simplifies the analysis quite a bit. You have to it's enough to focus on this one. And so here is the result for m equals 2. So you have a power of the Laplacian. You perturb it by c divided by mod x to the power 4. You define it on C0 infinity of Rn minus the origin, because that's our singularity. And then this object is essentially self-adjoint in L2, if and only if the constant c satisfies these inequalities that you see depending on dimension. So there is a particular one for the dimension between 2 and 5, and then another one for dimension larger or equal to 6. Once more, you can ask, of course, what happens if c is 0? Well, in that case, you would ask yourself, if you take the square of a Laplacian, when is it essentially self-adjoint? On C0 infinity of Rn, if I take out one point. Again, which one here, it doesn't matter, so we may as well take out the origin. And the answer is, if and only if the dimension is larger or equal to 8. So I remind you, when m is 1, we had n larger or equal to 4. When m is 2, you get 8. Now, I'm not going to give you many details, just a result for m equals 3. So here now you have a cubic power of the Laplacian. So it's c over mod x to the power 6. And again, you get essential self-adjointness in L2 when you define this operator on C0 infinity of Rn minus the singular point 0. This somewhat unwieldy looking inequality for C. Again, you have to distinguish ranges of dimensions. So 2 to 9, you get one formula, and larger or equal to 10, you get another one. And now you can ask again, of course, your question, what happens if C is 0? And then you suddenly realize the n has to be larger or equal to 12. Now remember, m equals 1, we got 4, m equals 2, we got 8, now we get 12. So of course it is m times 4 in general. And I should say the following. While m equals 1, as I said earlier, is a classical result, so this is textbook material, I'm not familiar with results for m equals 3, and even though it should be well known, I'm not even sure I know anything about m equals 2. So if there's anyone in the audience who does know or has seen a reference like that, please do let me know. So let me just give you one now kind of negative result before we move on to other objects. So so you could ask the following natural question after the examples I showed you. Suppose you have the mth order situation, or 2mth order, because it's the Laplacian to the m. You perturb it by c times mod x divided by 2m. And you ask again the usual question, are we essentially self-adjoint on a half-line? And is it an if and only if statement for C? Well, turns out the answer is no. So this time in multi-dimensions, you can have islands of non-essential self-adjointness. In this particular example that we found, we had to take m equals 5. It happened in dimension 20. And then it turns out this operator is essentially self-adjoint if and only if you are between alpha and beta or higher than gamma. Now, all these numbers are different from each other, all real, of course. I have explicit, well, approximate results for them below. And there is, of course, a gap now between the open interval beta gamma is now what I would call an island of non-essential self-adjointness. So one should not always expect an if and only if result in the half-line. It's more complicated than that. Okay, so let me go to the next part. We're going to look at fractional powers of the Laplacian. So far we did integer powers. Let's try fractional powers. So minus Laplacian to the s. S is a strictly positive number. And also, I would like to greatly generalize what we just did, because we looked at C0 infinity of Rn minus the origin, because we had a singular situation, of course, at the origin. Now I want to first look at just the Laplacian to the power s, no additional c over x to the 2s or so, just the Laplacian to the s, but I'm going to define it on C0 infinity of Rn minus a discrete set. And this set is otherwise arbitrary. So the only thing that, of course, defines a discrete set is that it has no finite limit points. So before we can say something about the essential self-adjointness of such an object in L2, so a fractional Laplacian defined on a fairly small set, C0 infinity of Rn minus x, let me mention a result that's in some sense interesting in its own. Everyone knows from distribution theory that if you're looking at a distribution that has a point support, so just one point, then the distribution necessarily must be a linear combination of the delta distribution and some of its derivatives. Now you might ask yourself, okay, what happens if there is 2 points, 3 points? What happens if you have a discrete set and your support is on that set? Turns out the same result is true. You can see it here in that theorem. It's still a linear combination of the delta distributions supported at points of your discrete set and their derivatives. So let me, I'm not going to tell you much about the proof, but for the following result, we had to use a fact like that. So here is something that regards fractional Sobolev spaces. I call them HS of Rn. They are defined as usual, typically via Fourier transform. So there is no surprise here. It turns out, though, when you have a discrete set X, then C0 infinity of Rn minus X is not always dense in such a Sobolev space. It is dense if and only if S is not too large. And not too large means it doesn't exceed n over 2 in the space dimension. So I have some arguments here that go into the proof, but I think I'll rather skip that and will now use the results of this type to get essential self-adjointness of either fractional powers of the Laplacian, the ones we started with now, or slight generalization. I add a mass term, and we have minus Laplacian plus m squared, so m is now a positive mass, and we take that to the power s. Everything is always defined on C0 infinity of Rn minus a discrete set. Okay, so how would one discuss self-adjointness of such an object? Well, to set this up, it's convenient to work with the associated graph Hilbert space. Let me first do this for closed linear operators in general, not yet applied to our situation. So let's call such a operator T. Let's look at operator T in a Hilbert space, and we look at its graph. So I have this strange symbol for pairs, ordered pairs in H cross H the Hilbert space, F in the domain of T, and then we look at F and TF, so the usual story about a graph. And this becomes a pre-Hilbert space with the usual scalar product. So you use the scalar product in H, and then you apply T on F and G, and you add the two scalar products. So in this setting, this object becomes a Hilbert space, sorry, a pre-Hilbert space, and it turns out your operator is closed, this is the point of the graph, if and only if it's actually a Hilbert space. So if your pre-Hilbert space is actually complete. So this is what's repeated here on the bottom. So we'll go via the graph Hilbert space to say something about self-adjointness of our fractional powers of the Laplacian, then minus Laplacian plus m squared, and then again a fractional power of that sum. So here is a little criterion star here that is very convenient to use, namely if T is closed, then a linear space, so I recall here the notion of a core of an operator. So a core for a closed operator is a dense space in that graph Hilbert space that we just introduced. And so when you restrict the operator to your set D and you close, you get back the original operator. Now, to show that something is a core, and for our applications, this set D will play the role of C0 infinity of Rn minus a discrete set. So in order to show that you have a core, and then eventually a domain of essential self-adjointness, you have to prove a statement like that. So if you find an element V that's in your domain, that's perpendicular in the graph Hilbert space sense to your set D, then V must be 0. So this is necessary and sufficient for having a core of your operator T. Well, now we're going to apply all this to our concrete situation. So either we look at a fractional power of the Laplacian, that's defined in H2 of S of Rn. You do this via Fourier transform, and then simply take the inverse Fourier transform, the Fourier transform. This is the unitary Fourier transform here, so it's normalized appropriately, of just a power to the power 2s because this is second order. And the same you would do with if you include a mass term. These objects, of course, are self-adjoint. So there's no question about essential self-adjointness here. No, we are self-adjoint on the full Hilbert space, which is not HS, but of course H2S because of the second order nature of the Laplacian. But now we're going to restrict these operators to C0 infinity of Rn minus a discrete set and ask ourselves, are we still at least essentially self-adjoint? Well, to set this up, we look at the graph Hilbert space, and let me, for simplicity, just do it for the power of the Laplacian, the fractional power of the Laplacian alone. If you add the m squared, the mass term, it's totally the same. So there's very little that changes, and nothing of substance changes. So I'm going to focus on the fractional power of a Laplacian only. So I redo the graph Hilbert space. Here's the scalar product. Because of this elementary inequality, you can see that actually the topology in the graph Hilbert space and that in H2S is totally equivalent. Because of these inequalities, we are talking about the same topology, which is crucial for the following. Because here you can see that, in particular, if you now want to conclude that a set D is a core for this object, remember this is self-adjoint. If it's a core, then it's a domain of essential self-adjointness. That's equivalent. This happens if and only if you found a set now dense in the Sobolev space. Actually, not HS, but H2S. Okay, and so remember we had a result earlier that C0 infinity of Rn minus x was in fact dense in that Sobolev space, so we can turn this around and rephrase this as an essential self-adjointness result for our fractional power of the Laplacian. So explicitly minus Laplacian to the s on this small set, C0 infinity of Rn minus x, x discrete, is essentially self-adjoint if and only if n is larger or equal to 4s. So again, n has to be large enough. You can also rewrite this as s is in the interval 0, n over 4. The 4 suddenly, instead of the 2 that we had earlier, comes, of course, because we had to change s into 2s, since this is second order. Now, this result here is, of course, absolutely classical and well known. If you don't take out anything, so if your set X is the empty set, then of course you are essentially self-adjoint for all S. Then there is no restriction for positive S, because C0 infinity by definition is dense in any HS. All right, so let me now do a little perturbation theory. Remember, I was starting out in the ODE and in the PDE case with adding C over mod X to some homogeneous power. Well, let's try the same with the fractional Laplacian, and by the same token with the fractional Laplacian amended with a positive mass term. So in order to do this, I'm going to apply perturbation theory. And so this goes back to Relicht, then Kato, but in fact what I really need is going back to a German mathematician, Wüst. And so here is the result that I'm going to use and then apply it to our concrete situation. So suppose A is self-adjoint in a fixed Hilbert space H. B is symmetric. The domain of B contains that of A. And suppose you have an inequality of this form. So in a sense, B is small compared to A, but not very small, because you see the constant here is 1. This was Wüst's contribution. If you had an inequality like that, no matter what B could be 0, could be positive, then the sum is essentially self-adjoint on the domain and on any operator core for A. Now, and so this works for whenever c is from -1 to +1. The -1 +1 comes from the 1 that I put in here that you don't see. Now, there is a slight extension of this. This goes back to Cardo and Relic. So if you restrict your C to the open interval, so you avoid ±1, then actually the sum is self-adjoint on the domain of A. And remember, A was self-adjoint on its domain. That is something we want to apply now. So what is it that we want to use here? Well, our A would be the fractional power of the Laplacian, again defined via Fourier transform, maximally defined via Fourier transform, then its domain is H2S. And now comes my singular additional potential coefficient. Let me call it B, because we just had A and B in the previous result, and everything depends on S now, so there's the subscript S. Also, B is maximally defined. So I take all those F's so that when I apply B on it, I'm still in L2. Okay. Now, somehow I need an analog of this inequality. Right? The inequality with a 1 here on the right-hand side. So B is somewhat small compared to A, but not too small. No epsilon here, just 1. Well, turns out there exists a fractional higher order, if you want Hardy, you could also say Biermann, Hardy, and Relic type inequality. Various names are associated to this. Here's the inequality. You see, I mean, again, I'm only focusing on the Laplacian and its fractional power. I could easily include a mass term. The inequality that I show you here is sharp in the following sense. The constant on the left-hand side is optimal, so you cannot use a larger constant than this. Then mod x to the -2s is no longer bounded by a corresponding power of the Laplacian on f. So this is an optimal inequality. And it goes back to Ira Herbst, but then it was discovered by Kovalenko, Perelmutter, Semenov, and also Yafaev has variations of it. These things are a little bit later. Herbst was first. So now what I'm going to do is I'm going to combine this theorem, this inequality, to get a result. So here it is. So this is a multidimensional one. So n is in n. S is again restricted, not too large, is between 0 and n/4. Sorry. And I'm asking myself, when am I essentially self-adjoint? Well, this time you can see there's no if and only if here. I'm applying perturbation theory. One should not expect if and only if results from perturbation theory, but there is a result. So this object, the fractional power of the Laplacian, plus this singular homogeneous object, restricted to H2S with a singularity, is essentially self-adjoint in L2 if the constant C is in the closed interval -1, 1. So the constant C here is what you just saw on the left-hand side. So this is the constant here, and it's probably repeated here. Yes, it's repeated here. So this is a result now that allows me to perturb fractional powers of the Laplacian with a strongly singular homogeneous potential coefficient, if you want. Now, here we had a result on essential self-adjointness. I can go to cores now, and it remains an essential self-adjointness result. And so I can, for instance, say, which is what we started out to some degree with, I can take the same object, so minus Laplacian, fractional power s, then this strongly singular homogeneous term, restricted now on C0 infinity, and it's also essentially self-adjoint in L2, as long as C is in the closed interval -1, 1, so not too large. Now I have a few more comments about this. Again, you cannot assume that the condition C in -1, 1 is optimal. However, what we had about S can be shown to be optimal, so it's not that bad. And in fact, one can see that the lower end of this interval for C is also optimal. It's just the upper end +1, of course, is not optimal. So that essentially concludes what I wanted to say. I have repeated what we really are aiming for, and this is still a work in progress. Let me say the following, though, at the very end here. Discrete for X is not crucial. So this is not the last word in this story. One can actually go further and take out not only discrete sets, but also suitably thin sets. And for thinness, there is a notion that of capacity, and in this precise context, a Bessel capacity that is associated with the power S that you see here. The 2 here comes from L2, so normally there's an SP for LP, Bessel capacity. And so, in fact, one can extend much of what I showed you to suitably thin sets in the sense that their Bessel capacity S2 equals 0. You don't necessarily get if and only if results, but you get results. And maybe at the very end, I'm going to show you a little what this is based on. So we have a few papers in this area fairly recently. So the first one appeared. The next one is 2 appeared. This one also appeared. And the fractional power results that I just talked about are jointly with Dorina Mitria, and they are in preparation. So we are finishing the capacity result in this context right now. And with that, I thank you.
Thank you so much, Fritz.
Should I stop sharing or?
Maybe somebody has questions. Might be good to have the slides open.
Okay.
Let me just stop the recording.